All right, so today we'll be looking at the tree diagrams, okay? And then we are also going to define what the complement of events is, okay? And then just on these two concepts, we are going to solve some um, sample exam questions, okay? So this is what we are going to do in today's lesson, okay? So I encourage you guys to ask, okay, in case you do not understand anything that I would explain, okay, make sure you ask and you learn. All right, so we start from the definition of what a tree diagram is, okay? So a tree diagram by definition is just a tool that is helpful in identifying all possible outcomes of an experiment, okay, especially an experiment that has two outcomes, okay. So these two will be very important for us to come up with the possible outcomes of that experiment. So these possible outcomes, we said they were what? Okay, if we get all the possible outcomes of an experiment, we said that was making what we were calling as the what? The sample space. Okay, that was making what we are calling as the sample space. So we can use a tree diagram to show the sample space of an experiment. Okay, so I'll give an example here. So let's say you toss a 1 kwacha coin. Okay, toss a 1 kwacha coin. Okay, so if you represent the possible outcomes of tossing this 1 kwacha coin on a tree diagram, it will be something like this. Okay, so you draw two lines, okay, that are going apart like that. Okay, so this one here will be the probability of getting head, okay, and then here it will be the probability of getting a what? A tail. So you can see that you can use this probability tree diagram here to find out the sample space, because we know that if we just toss this 1 kwacha coin once, okay, our sample space will either be head or what? Or tail. So this will be our sample space. So we can represent this sample space on a tree diagram like that, okay. And then even if we have more than one tosses of this coin, okay, we can still be able to use this concept of a tree diagram, okay. So let's say, for example, you toss your coin twice, okay, and then they ask you to find the total outcomes, okay. So if this is your coin, then you toss it for the first time, okay, it's either you land on the head or you land on the what? The tail. And then they tell you to toss this coin again, okay. So if it first landed on head, okay, if you toss it for the second time, it will either land on what? Head or tail. Even this one here, if it landed on tail, it can go on and land on what? Head, or it can go on tail. So this here, we can divide it like that. So this will be our first toss, and then our second toss, okay, and then we can even add a third toss here in red, okay. So this one that landed on head can go and become tail and head. Even this one here will still be tail and head. Even this one here, it will still be head and tail. Even this one that landed on tail here can go and land on what? Head or even tail, okay. So this tree diagram here, we see that it's very important when you have a number of experiment that you are doing, okay. If you have a number of experiments that you are doing consecutively like that, okay, it's a very important tool that will help us determine all the outcomes of a what? An event, okay. So on the next here, I have an example question. They're saying construct a tree diagram for the sample space, okay, that describes a 3-child family according to the gender of the child with respect to the birth order, okay. So we know that if you want to have a child, okay, it either means that you are going to have the child who is a boy, or you have a what, a girl. So according to gender, the child can either be a girl, or it can either be a what, a boy. Okay, so here they are asking us to draw a tree diagram for a 3-child family. So meaning the first round here, okay, or the first um, probabilities that we're going to get here will be for um, will be for the firstborn here. Okay, so the firstborn of that family will either be a girl or a boy. Okay, and then when they decide to have another child, okay, again the chances are that child is a boy or girl. So let me use yellow here. So this here we can say is the firstborn. So let's write firstborn here. Okay, firstborn. And then now we have another child with a second boy. So if the first child was a girl, it means the second one can either be, okay, can either be a girl again, or the child can be a boy. Okay, if the first child was a boy, the second one can either be a boy or girl as well. Okay, so this one in yellow there, I'm going to say that's the second born. Okay, and then from there we can also come up now with the probabilities of the third born. So the third born, we are going to go to this point here. Okay, so this point we are the girl. So from this girl, it means that when we have the third born there, it can either be that the third born is a girl as well, or it can either be a what, a boy. Even this one here is a boy, can either be a girl or a boy, like that. Okay, so even this one here was a girl as the second born, okay, can go on and become from this girl here, you can go on and have a girl again, or you can have a what, a boy. Okay, and then from the second child who was a boy, you can also go on and have a girl or another boy, like that. Okay, so those probabilities that I've drawn in blue here are going to represent the what, the third born. So we've constructed what they wanted us to do here. Okay, so a 3-child family according to the gender with respect to the birth order, like that. Okay, so the firstborn can either be girl or boy. Okay, and then we just follow it like that. So this here is a very important description, okay, of the total sample space that you can have in a what, in an experiment. Okay, all right, and then we move forward to talk about the complement rule of events. Okay, so from your first here, we know that the complement just simply means, okay, if you are describing the complement of a set, then it means that you are looking for those elements that are not you're looking for those elements that are not in the what, in the stated set. Okay, you are looking for those elements that are not in the stated set. So for example, if let's say set A has elements 1, 2, okay, and then the universal set, maybe it had 1 to 5. Okay, 1, 2, 3, 4, 5. Okay, if this is the universal set and this is A, we know that our A complement will be what? Okay, our A complement will just be 3, 4, 5. Okay, so even when we are talking about probabilities here, okay, they are what we call as complement events. Okay, so I've written down the definitions here and the formula that we are going to be using to find these probability events. Okay, so I was saying the complement of an event A in a sample space S is denoted by A complement, like that. Okay, and is a collection of all outcomes in the sample space A that are not elements of this event A. Okay, and then if A is an event and A complement is its complement, okay, then the probability of the complement event happening, okay, is just equals to, okay, someone has raised their hand. You're free to ask.
These notes, where can I get them from?
I shared the link where you can find all the notes. You didn't see the link in the group?
No, I did, but the notes were a bit different from the ones that you are giving us, right?
Oh, okay, okay. So then the notes they can be a little bit different, but the meaning is the same actually.
It's the same.
Yeah. Yeah.
Alright.
All right. Okay, so I was explaining that when you want to find the probability of a complement event, okay, the probability of a complement event is just the same as 1 minus the probability of that event happening. Okay, simply meaning that the probability of something not happening, okay, is actually equals to 1 minus the probability of it what happening. So this rule here is very important, okay, because there are some scenarios that you are going to be given where you are required to find the probability, okay. If you follow the straight path uh, rule for you to find the probability of this A complement, it will be a very long process, okay, and it will be what difficult. Okay, so what do we do in order to cut it short or to find a better way to find the probability of a complement event? Okay, we use this formula here. Okay, so this formula will be very important. Okay, just know that the probability of a complement is the same as 1 minus the probability of A. Okay, so this formula is useful when directly finding probability of an event that is difficult or what tedious. Okay, so let me give an example here. So we have these examples here. Okay, so the examples they're saying if the probability of A is 0.2 while the probability of B is 0.3, okay, find the probability of A complement. Okay, so we know that the probability of this A complement will just be equals to 1 minus the probability of what? A. So probability of A complement will just be equals to 1 minus 0.2, and we see that here we are going to get 0.8. So this 0.8 will be the probability for the what? A complement. So this was A. And then for B, okay, we are finding the probability of B complement. So we are still using the same formula. So B complement is equals to 1 minus the probability of what? B. So the probability of B there is 0.3. Okay, so this will just be 0.7 like that. Okay, so this will be the answer there. So we are done with the first question there. All right, and then let's look at the second one there. Okay, so the second one is in a more of applied way. Okay, so they are saying, suppose you know that the probability of getting the flu this winter is 0.43. What is the probability that you will not get this winter? You will not get this flu, I mean. Okay, so the probability that you have no flu, I'll just write no flu here, is the same as 1 minus the probability that you have flu. Okay, so this very simple rule, guys, that I'm talking about, it's very important in probability, even when you go to your statistics. Okay, so we are going to say 1 minus the probability of the flu is just 0.43. So from here we are going to get what? Okay, so you just subtract. So we are going to get is it 0.76? Okay, 0.5657, I mean, so 0.57, that will be our answer here. So that's the probability that you will not get the flu during the what? The winter. So the complement event what we are seeing here is that the complement events, when you add them, they should always add up to what? To 1. So if you get 0.43 and then you add 0.57, you're going to get 1.00. Okay, so this is the rule that is expected. Okay, so when you get the probability of the complement events, always make sure that when you add them, they give you 1. Okay, even here we had 0.2 plus the probability of the complement was 0.8. When we add this, we are going to get 1.0. Okay, so always that's how it is. If this and that event are complement events, okay, then the probability when you add, they should be what? Should be 1, like that. Alright, so those are the two concepts that I wanted to teach you guys. Okay, and then now we can look at some questions based on the tree diagrams and the complement events. Okay, so let's look at those questions now. So exam sample questions here, we have 2 of them. Okay, I know you are familiar with this first one here because you did a bit of it at grade 12, and then there's also this question here that is totally different from whatever you did at grade 12. Okay, so we are going to solve these 2 questions, then at the end I'm going to give you an assignment, so make sure you try it out, okay, to see if you've understood the concept. Okay, so let's solve question number 1 here. Okay, so question number 1, they're saying a bag contains 8 red marbles and 12 blue marbles. Okay, and then they are saying Paul selects 2 marbles without replacement. Okay, so the first question is, what is the probability of selecting 2 blue marbles? Okay, so what we see is that for us to answer this question, we'll have to draw a tree diagram. Okay, we have to draw a tree diagram. So how many marbles has this guy Paul selected? Okay, Paul selects 2 marbles, so it means you have two selections there. Okay, there's the first one and then the second one. So for the first one, okay, if I'm here for the first one, I'll select like that. Even here I'll select like that. Okay, so we can say that this one here represents blue and then this one represents red. Okay, so this is my first selection, and then my second selection will be from this red. Okay, I can either have another red or I can have blue. Okay, even from this blue, if I select a second marble there, okay, it can either be red or it can be blue again. Okay, so now what is the probability of getting a red marble? Okay, so you just go to what you've been given here. So we have red 8 marbles and then we have 12 blue marbles there. So we are going to add to find the total marbles. So total marbles will just be equals to 8 plus 12. So this here is going to give you a 20. Okay, so to find the probability of red, we're just going to be do the favorable marbles that we want to find the probability for, which are red. So they are 8, and then we divide by the total probability. So we can reduce this. Okay, so this will be, you divide both sides, both the numerator and the denominator by 4. What are we going to get? We are going to get 2, and then here we're going to get 5. Okay, so the probability of obtaining red there will just be 2 over 5. So I'm going to write 2 over 5 here. And then what is the probability of getting blue? Okay, so the probability of blue is just going to be equals to, okay, the probability of blue will just be equals to the favorable marbles, okay, that are blue marbles. So we're going to write 12 divided by 20. And then let's divide both of these by 4. So if I divide 12 by 4, I'm going to have 3. If I divide 20 by 4, I'm going to have 5. So it means the probability of obtaining a blue marble is what? 3 over 5, like that. Okay, so now you have to pay attention here. Okay, you have to pay attention here based on what you've been taught. So here they're saying Paul selects 2 marbles without replacement. Okay, so meaning if you select the first marble, you're not taking it back, okay, into that bag. You are holding on to it, okay. So when we'll be now making this second selection, okay, it means the total marbles in that bag have reduced. So the total marbles here were 20. Okay, after your first selection, it means the marbles have reduced, right? Okay, so if you picked a red marble at first, okay, it means from the 8 that we have, someone has a question? I can hear some backgrounds. Oh, okay. So if your first pick was a red marble here, okay, it means from the 8 marbles, you are now remaining with what? 7. So we can just reduce this fraction here, okay. So if my first one was a red marble, it means now when I do my second pick, okay, it will just be 1 over 4. That would be the probability, right? Okay, so the total has reduced. Even the favorable, which are 2 in this case, have also what? Reduced. So we're going to have 1 over 4 there. And then going to the blue, okay, if your first pick was a red marble, it means the blue marbles are still the same. Okay, so the blue marbles, we said its probability is 3 over 4. So we're going to write 3. Okay, so what has changed here is just the total, but the blue marbles, the probability is still the same. So we are going to write 3 over 4 here. Okay, because the total has changed. Okay, but the blue marbles, the number is still the same. So even here, if we first picked the blue marbles, okay, if we first picked a blue marble here, it means its probability is going to reduce. So we are going to have 2 over 4. Okay, and if our first pick was a blue marble, it means the red ones are still intact. So we are going to have 2 over 4 as well. Okay, so we have kept the 2 here, which is these 2. We just changed the total there. Okay, and then from this tree diagram now that we've drawn, we can come up with the probabilities that they are asking. Okay, so let's follow some path here. So if I follow this path for red and red, what am I going to get? Okay, I'm going to get 2 over 5 multiplied by 1 over 4, which will be 2 over 20. Okay, so 2 over 20 if I get red, red. So you just multiply this, you multiply it with that. Okay, what if I go red and then blue? If I go red and then blue, it will be 2 over 5 multiplied by 3 over 4. So this here will give me what? It will give me 6 over 20. Okay, and then if I go, my first pick is blue, then a red one, okay, it's just going to be equals to, I have 3 over 5 multiplied by 2 over 4. So this here will be the same as this. So it will be 6 over 20. And then this here will be equals to, if I pick a blue one and again a blue one here, okay, it will be 3 over 5 multiplied by 2 over 4. Okay. So this is the same as 6 over 20 as well. So we have the probability of getting red, red, red and blue, blue and red, blue, blue. Okay, and then now we can go back to the questions and try to answer them. Okay, we can go back to the questions and try to answer them. So the first one, they're saying, what is the probability of selecting 2 blue marbles? Okay, so we're going to say probability of selecting 2 blue marbles, which will just be probability of blue and blue, is equals to, okay, so blue and blue will just be equals to what? 6 over 20. So 6 over 20, you can just reduce it into its lowest terms. So it will be 2 divided into 6, it will be 3, and then 2 into 20, it will be 10. So this is the probability. If you want, you can represent it as a fraction. Okay, so the probability of selecting 2 blue marbles will just be 3 over 10 there. Okay, and then B, so this was A, and then B, we are told what is the probability of selecting at least 1 red marble. Okay, what is the probability of selecting at least 1 red marble? Okay, so what are we going to do in order to find that? Okay, so the probability of selecting at least one red marble is, okay, we can go, we can select red and red, or red and blue, or blue and red. So in these three scenarios here, we see that we have at least one red what marble. So to find the probability, we are just going to add this probability for red plus the probability for red and blue, and then the probability of blue and red. Okay, and then we find our answer. So let's add. So the probability of at least one red, okay, is just going to be equals to the probability of getting both marbles as red, which will be 2 over 20, plus the probability of getting, on your first try you get a red and then a blue one, so it will be 6 over 20, plus the probability of getting a blue and then a red one, then it will be 6 over 20 again. Okay, so we can add this. So the common denominator is 20, so we add 2 plus 6 plus 6, so we are going to have 14 there. Okay, so this 14 over 20, you can reduce it. So 2 into 14, it will be 7 divided by what? 10. So this is the probability of selecting at least one marble. So now notice that we can also solve this question using what? The complement rule. Remember the complement rule that I explained earlier? Okay, so let's keep this answer 7 over 10, and then we try to use the complement rule. We see if we are going to get the same answer. Okay, so probability of at least, okay, one red, this is what we are finding. So this probability of at least one red is going to be equals to 1 minus the probability of getting no red at all. Okay, so what is the probability of getting no red at all? Is just the probability where we get two blue marbles. Okay, so we're going to say this is equals to 1 minus, what is the probability of blue and blue? Okay, the probability of blue and blue is 3 over 10. We found it here. Okay, so this will just be equals to, so this 1 is the same as 10 over 10. So the common denominator there will be 10, and then 10 minus 3, we see it's 7. Okay, so we see that 7 over 10, if in there we found 7 over 10. So which one is a shorter method? Okay, we see that the one where we use the complement rule is the shorter method. Okay, so there are scenarios where it's basically impossible to find the answer using the straightforward method. You just have to use the complement rule. So make sure, guys, you understand this complement rule, because it gives you the answer much faster, much quicker, and in an easier way. Okay, so we can solve this b here in two ways. I've shown you both ways. So the one that I recommend is this one here. For what? For the complement rule. All right, and then let's solve c. Let's solve c. So C, now we are solving something different now. Okay, so for C, they are saying what is the probability, okay, of selecting a red marble first and then a blue marble. Okay, so that probability of selecting a red marble first and then a blue marble is equals to, we just get what is here. So red, blue, it was what? 6 over 20. So this is just 6 over 20. Okay, so this will just be 3 over 10. That's all. Okay, that's all. So that's the probability of getting a red marble first and then a blue. So in this C here, there is order that we are following. Okay, we get first the red marble and then the blue one. Okay, and then you are going to see that on D, it's quite the opposite. Okay, so on D there, they are saying what is the probability of selecting a red and blue marble. Okay, so in D here, there is no order, so we can first select a blue and then a red, or a red and a blue. The order doesn't matter. Okay, so what is the probability of selecting a red and a blue? We're just going to add these two here. Okay, the probability of red and blue plus the probability of blue and what? Red. So let's find. So the probability of getting, okay, so the probability of getting blue, red, or probability of red, blue. So this here is just going to be equals to, okay, blue, red, we see it's 6 over 20 plus red, blue is also 6 over 20. So this actually will just be 12 over what? 20. So we reduce this, is going to be 4 divided into 12. You're going to get 3 over 4. Okay, so this here is the probability of selecting a red and blue marble. Okay, so any questions there? Any questions there, guys? Okay, so if there are no questions, I'll move and solve the last question. Okay, so the last question, please pay attention. Okay, so on this question we have that, okay, find the probability that at least one head will appear in 5 tosses of a fair coin. Okay, so when they say a fair coin, they mean that the probability of it landing head or the probability of it landing tail is the same. Okay, so immediately you see fair coin here, just know that the probability of head is equals to the probability of tail, which will just be what? 1 over 2, like that. Okay, so how are we going to find this probability in 5 tosses? Okay, we are going to use the tree diagram. Okay, we are going to use the tree diagram and the complement rule. Okay, so if I can come up with a tree diagram here, okay, so we're going to say the first toss, okay, you can either land tail or head. Okay, so what about the second one? Okay, so the second one we can also land head or tail. Even there, the second one we can still land head or tail. Okay, and then the third toss we are going to go from head. Okay, from that head we can go to tail. So head, tail. Even this one here we are going to go head, tail. Okay. Okay, so this is the third toss. So head, tail, head, tail. Even this one here we are going to experience head and tail. Okay, and then we see that we're just going to continue this same process. Okay, we'll just continue this same process. It means in the fourth one we are going to have head, tail. Okay, just like that. Even here you add for the tree diagram like that. Okay, so now notice what the question says. The question says find the probability that at least one head will appear. Okay, so so here we're just going to use the complement rule to find this answer. So what are we going to do, or what does it mean at least one head will appear? Okay, so the result that we can get from the 5 tosses is that the first one can be head, the second one can be head, the third one can be head, fourth one can be head, even the fifth one can be what? Head, like that. Okay, so there's just only one situation where we won't have a head in our 5 tosses. Okay, so that situation is when you obtain tail, 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 tail. So if you have this situation here, it means you have no head in your toss, in your 5 tosses. Okay, but the rest of the tosses, they're just going to be a combination. It either be head, tail. Okay, there will just be a head somewhere, so it can be head, tail, 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 tail. Okay, or it can be tail, 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 and then a head at the end. So in all other combinations that are remaining, okay, you are going to have a head there. So there's just one scenario where you're not going to what? Have a head, and that scenario is what? Tail, 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 tail. So we are going to use, or we are going to find the probability of this tail, 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 and then we are going to subtract it from 1. to find the probability that at least one head what appears. So we are going to say, let me clean this up. Okay, I was just using it to explain the concept. So we are going to say this. So the probability of at least, okay, one head is just equals to 1 minus the probability of no head at all. So the probability of no head at all is tail, 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 tail in your 5 tosses. Okay, so now how do we find the probability of this tail, tail, tail? We need to find, first of all, the the total uh, outcomes of the probability, okay, of the experiment. I mean, we have to find the total outcomes of the experiment. So probability of tail, 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 tail is just going to be equals to, okay, so this is just one of the possibilities. So we're going to write 1 over, okay, and then here they're saying 5 tosses, okay. So we see that from these 5 tosses, each of those tosses, okay, will have two outcomes to it. Okay, so the first experiment, you have a tail and a head. So 1, 2 you count, and then the other one to be 1, 2 there, 1, 2 there. So it will be 1, 2, 3, 4, 5, 6. And then from this again you get 2, from this you get 2. So we see that in each of those stages, okay, it's increasing by 2. The number of outcomes is increasing by 2. So in the first experiment you're going to have 2 outcomes. In the second one you're going to have 4 outcomes. In the third experiment you're going to have 8 outcomes. In the fourth one you're going to have what? 10. In the fifth one, what are we going to have? We are going to have 8 multiplied by 2. Oh, this here we are supposed to have 16. So in the fourth one we are going to have 16, and then at the end there we're going to have what? 32. So there are 32 total outcomes in the what? In this experiment. Okay, so we are going to say the probability of obtaining 5 tails is just equals to 1 over what? 32. If you want, you can just say the total outcomes, okay, of the of this experiment is equals to, okay, so we know that a coin has 2 outcomes, right? So you're going to write 2, and then you are going to say to the power how many times you've tossed that coin. Okay, so just be 2 to the power 5 here, which will still give you a 32. So 32, okay, is the total number of outcomes, and then we just want to find the probability of one event there, which is tail, 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 tail. Okay, so we see that the probability there of getting 5 tails will just be 1 over what? 32. So immediately we have the answer for this, then we can have the probability of at least one head there. Okay, so let's find it now. So the probability of at least one tail will just be equals to 1 minus the probability of having 5 tails, which is 1 over what? 32. So here just subtract. So this 1 can be this written as 32 over 32 minus 1 over what? 32. So what do you get here? You get 31 over what? You get 31 over 32. So 31 over 32 is the probability that you are going to have at least one head when you cause a coin 5 times. Okay, so any questions there, guys? Okay, if there are no questions, then I'll end here. But as I said, I have an assignment for you guys. Okay, so this is the assignment here. You can take a screenshot and then you try to solve it. Okay, try to solve it, and then you can send me your solutions so that I see if what you'll be doing is correct or it's not. Okay, otherwise, if there are no further questions, then have a blessed night.